Today's lesson, 1.3, is about powers and exponents. So the reason I've left this vocabulary slide in here is because there's some basic parts of a power. When we look at a power, it's the whole thing, right? 5 to the second power. There are two parts. You have your base, which is the large number. The base is the large number, which can be described as the repeated factor. And the exponent, which is basically telling you how many times the base is a factor of itself. So if you want to label the power in your notes and then point to the parts, then you'll know what it is. The exponent is the small number, the base is the large number, the power is the whole thing put together. So example 1, we're going to write the product as a power, meaning it needs a base and an exponent, and then we're going to describe the power in words. So when I look at the first one, A, I see that I have a repeated factor of 10. The repeated factor is the base. So first, I write the base, and it's going to be a little bit larger than I actually write the exponent. Since it's repeated 3 times, the exponent is the 3. Now, when I describe it in words, I can say two things. I can say 10 to the third power. And for the exponent of 2 and the exponent of 3, we have some special names. I could also say 10 cubed. Either of these would be acceptable. When I look at B, the parentheses were kind of helpful because of the decimal point. A lot of times when we're working with decimals, we use parentheses more than dot multiplication because we don't want to confuse the decimal point and the dot multiplication. So I see 4.3 as my repeated factor, and it's repeated 2 times. So I will keep the parentheses around it so that it doesn't mistakenly look like the 3 is the only one raised up. It's the whole decimal. And again, that is a factor 2 times. So I can, in this, sometimes you can just write out the number. You don't have to list it out with words. So 4.3 to the second power, or again, this could be 4.3 squared. Those are the only 2 exponents with special names. Everything else will be the ordinal number and the word power. So when we look at C, I see a factor repeated 4 times. The factor is the variable x. So I have to write it as a power, so I use the variable x and my exponent of 4. And when I put it into words, I'll say x to the fourth power. Example 2, let's evaluate when f is equal to 5. So, interesting. It's going to go in parentheses and then be raised to a power. So we're going to substitute in for this f the number 5. So I'll rewrite it. Since the power of 3, the exponent of 3, is outside the parentheses, order of operations tells us we have to do what's in parentheses first. So I want to take 5 minus 2, which is 3, and that is what's getting cubed, plus 7. 3 to the third power is equal to 27. So I should get 34 for my answer. Okay, in this case we're going to evaluate an expression, order of operations. So we're just going to follow the basic order of operations, which again are, we first do parentheses, then we look to evaluate the exponents, then we'll do multiplication, division left to right, and then addition, subtraction left to right. So with our parentheses, we know that we want to rewrite this, and we'll do 4 to the third power minus 28, and we have 8 to the second power. So this becomes 4 times 4 times 4. And then this becomes 8 times 8. When you take 4 to the third power, you'll get 64. When you take 8 times 8, you get 64. Now the key here is to do this left to right. So 64 minus 28 is 36. When you add them together, you get 100. At this step, if you would rather put it in your calculator, depending on the calculator you have, the one that we recommended, the 30XA, you could put in the 4, then hit the key that is the Y to the X button, and then put in the 3. If you're working on a different model calculator, you would put in the 4 and then hit the key that has the little pointed up arrow, which is giving this, so it'll do a superscript or the exponent, and then putting in the 3. So you'll have to check with your technology on your calculator to see which one of those will help you as a time saver, especially when our exponents get really, really large. We don't want to miscount the factors, so sometimes using that function on the calculator will help us as a time saver. All right, so let's see about this. Do you think that these will all have the same value or different values when f is equal to 5? Okay, when we look at the first one, we know that we are going to be taking, we'll substitute in the 5. So we have 5 times 5, which equals 25. In the second one, we have 2 times 5 squared, or 2 times 5 times 5, which will equal 50. And in the third one, because of the parentheses, we will take 2 times 5 first and square that. So it is actually 10 squared, or 100. So again, be really, really mindful of what the order of operations are telling you, and you always do exponents before multiplication in this step, and the only thing being raised to the exponent is the 5. But when there's parentheses around it, you do what's in the parentheses first and evaluate the exponent second. All right, and finally, we'll watch a video of a repeated multiplication using exponents.
One human skin cell splits into 2 cells every day. So if we start with just 1 cell, 1 day later there will be 2 cells. How many cells will there be 5 days later? What's your guess? Let's explore. In this lesson, you will learn how to represent repeated multiplication using an exponent, also called a power, by exploring a model of cell division. Remember, we can use a table to explore relationships and discover patterns. So let's use a table to explore this pattern. We can list how many days later it is in the left column and the number of cells in the right column. Remember, we started with just the 1 cell, so we won't put a number there. We'll just put the word start. On that day, we had the 1 cell. 1 day later, the 1 cell has split into 2 cells. The next day, so 2 days later, the 2 cells have split into 4 cells. Do you think you see a pattern yet? How many cells will there be 3 days later? Is it 6? Some might think it is 6 because it looks like we are adding 2 cells every day, but let's draw it out just to be sure. When we take each of the 4 cells and split them into 2, we don't have 6 cells, we have 8. We are quickly running out of room to draw any more cells, so let's see if we can figure out the pattern. What do you notice? Do you see that since the number of cells doubles each day, we can multiply the number of cells from the previous day by 2 to get the current number of cells? The 1 cell multiplied into 2, so there were 2 cells. Then those 2 cells each multiplied into 2 more, so there were 4. Then those 4 cells each multiplied into 2 more, and there were 8. So to get the number of cells on day 4, we'll just multiply 8 times 2 and get 16. Then to get the number of cells for day 5, we'll multiply 16 by 2 and get 32. So back to the original question, if a human skin cell splits into 2 cells every day, how many cells will there be 5 days later? There will be 32 cells 5 days later. The way we just explored this pattern makes it seem as though to find how many cells there were a certain number of days later, we would need to know how many cells there were the previous day. But let's add an extra column to our table and see if we can discover a different operation. At the very start, we did no operation. We just had 1 cell. But then 1 day later, we multiplied that 1 cell by 2. Since multiplying by 1 does not change anything, we'll just leave a 2 here. 2 days later, we multiplied those 2 cells by 2, and we had 4 cells. But let's just leave the 2 times 2 here to continue exploring the pattern. 3 days later, we multiplied by a third 2 to get our 8 cells. 4 days later, we multiplied by a fourth 2 to get our 16 cells. And 5 days later, we multiplied by a fifth 2 to get our 32 cells. See how quickly we've gone from just 1 cell up to 32? This type of growth that is based on repeated multiplication is called exponential growth. The root word here is exponent, because we can express exponential growth with a new operation called exponents. With an exponent, we can summarize a multiplication statement of 2 times 2 times 2 times 2 times 2 as 2 with an exponent of 5. In this example, 2 is considered the base, while 5 is considered the exponent, or power. An exponent, also called a power, tells you how many times to multiply a base number by itself. So for instance, when the base is 2 and the exponent is 5, we multiply 2 times itself 5 times and get 32. Or if we wanted to find out how many cells there were 10 days later, we could represent this as 2 to the 10th power because it would indicate we are multiplying 2 by itself 10 times. Here's another quick example. Evaluate 5 raised to the exponent of 3. Some students may multiply 5 times 3 here and get 15. But 5 to the third does not indicate we have 3 sets of 5. So that is not correct. A base of 5 raised to an exponent of 3 tells us to take a single object, here represented by a black dot, then multiply that by a factor of 5 3 times. The first time we end up with 5 red dots. We multiply those 5 red dots by 5, we end up with 25 green dots. And when we multiply each of those 25 green dots by 5, we end up with 125 blue dots, a lot more than 15. It's not always convenient to create such a visual, so when we see 5 to the third exponent, we can simply multiply 5 times itself 3 times. This simplifies to 25 times 5, which simplifies to 125. So 5 to the third power is 125. In this lesson, you have learned how to represent repeated multiplication using exponents, also called powers, by exploring cell division.